Alright, for this next example, example 2, we are to determine the Taylor series of e to the x, but about a different center. The previous example, we essentially determined the Maclaurin series for e to the x. That is, we figured out the Taylor series for e to the x centered at x equals 0. So, because of this, the fact that we are centering about a different point, x equals negative 2, I'm not sure if I said positive 2 the first time, I meant to say negative 2. This will just make some of our calculations a little bit slightly more tedious, just because we're going to have this, we're going to be plugging in negative 2 instead of plugging in 0. So, yeah, our expressions will just look a little bit slightly more complex, but not much more at all. So, what we'll do is our table. So for our table, again, left column, we don't really need to make the table for e to the x because its derivatives are so trivial, but it's a good habit to be in, especially when we get to more complex functions. So we'll create a table. Leftmost column we'll make n, and we'll just start with 0. Middle column, we will have the nth derivative as a function of x, and then the third column, we will have the nth derivative evaluated at our center, which in this case is negative 2. So the 0th derivative is just the original function. And then if we plug in negative 2, well, we have e to the negative 2. First derivative, so n equals 1 now, so we take the first derivative, well, that's just e to the x. So plugging in, we have negative 2, and it doesn't take long for us to see that the nth, in general, the nth derivative is just e to the x, and the nth derivative evaluated at negative 2 is just e to the negative 2. So so e to the negative 2 is just a little bit more complicated than e to the 0, which is 1. So barely more complicated. So our Taylor series would be the series from n equals 0 to infinity. Of course, we have our nth derivative at our center value over n factorial, and then x minus our center to the n. So replacing in what we have for our series, we will obtain series from n equals 0 to infinity. All of our nth derivatives evaluated at negative 2 are just e to the negative 2, all over n factorial. And then this term will have x minus negative 2, so plus 2, x plus 2 to the nth power. So that is our our Taylor series for e to the x centered at negative 2. So it differs in that our coefficients for the Maclaurin series were e to the 0, so this was just a 1, which is nicer looking, and because our center was 0, this term is just x to the n. So this looks slightly more complicated than what we had for the Maclaurin series. In the previous example, the Maclaurin series for e to the x is x to the n over n factorial. And if we actually perform a ratio test on this to determine the radius and interval of convergence, which we can do extremely fast. So the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So this would be x to the n plus 1, so I'll just break that up into x to the n times x, all over n plus 1 factorial, which I'll break up into n plus 1 times n factorial, and then dividing by that fraction will reciprocate and multiply. Canceling the commonality, so n factorials and x to the n's cancel. And then that absolute value really only needs to stay on the x because n plus 1 is that's positive. So the limit here is 0. So this means rho for the ratio test is 0, and 0 is always less than 1. Since this limit, the ratio rho, doesn't depend on x, this implies our radius of convergence is infinite, since it would converge no matter what the value of x is. So if our radius of convergence is infinite, that means our interval of convergence is the entire real number line. So whenever you have a series that converges over the entire real number line, it's customary to use the Maclaurin series as opposed to other Taylor series that are centered at different values. So here there really is no great reason to use the Taylor series of e to the x centered at x equals -2, unless in application you were needing to approximate values that are very close to e to the -2, in which case if you center your Taylor series at x equals -2, then your approximations wouldn't need to include as many terms. So for instance, if to get the accuracy that you need, the desired accuracy for the Maclaurin series, maybe you need to include, let's say 10, this converges very fast, but let's say you needed to include 10 terms to get the accuracy needed if we're using the Maclaurin series. So you're estimating things at x equals -2, you would need 10 terms if you center your series at 0. Whereas if you were to center your series near the value where you are approximating, then perhaps you might only need like 3 terms. So based on a case-by-case basis, it might be better in application to use a Taylor series centered at some other value other than 0. But if you are doing this from a theoretical point of view, there is no benefit, because the series converges, has an infinite radius of convergence, so might as well just use the Taylor series that has the simplest form, the cleanest form, and that would be the Maclaurin series. Okay, example 3. Determine the Taylor series of f of x equals x minus x cubed with center, again, c equals -2, and then determine its radius and interval of convergence. So this is a little bit of a trick question, so to speak. If you watched the very first video from this section 10.7, it was a lengthy video where I went on Desmos and did some worked on building some graphical intuition behind why we would use Taylor series to approximate functions, and how we are essentially taking a function and then using the function and its derivatives, extracting information about the function at a location, and then using that information we can, depending on some properties of the function, we may be able to uniquely define the function everywhere if it has an infinite radius of convergence. Well, another perspective, instead of approximation or extracting sort of information from the function, we could think of a Taylor series as a way of inputting a function. So taking some function and then feeding it into a machine. This is my schematic for the Taylor series machine. So we input a function into this machine that spits out the Taylor series. Then we get the Taylor series for f of x. Which is, of course, the series from n equals 0 to infinity, the nth derivative at our center value over n factorial x minus our center c to the n. So we can think of this as essentially a process that takes something, sine, cosine, e to the x, natural log, tangent, some function that's complicated, sufficiently complicated, and then it allows us to think of it approximately as a polynomial. So in words, a Taylor series is, in one sense, a way to, I'll put this in quotations, convert, or it might be a better word is associate, is to convert / associate every function with and again quotations because this is not really well defined, I'll say in quotations an infinite degree polynomial. For instance, sine of x. If we won't go through all the motions of finding the Maclaurin series for this, we would have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And then this continues forever. This converges fairly fast due to the factorials. So in this way, we can think of sine of x as approximately this polynomial. Now this is infinite, it goes on forever and it converges, but it is a way of sort of associating to every function a polynomial. So if that's one way or one perspective we can have on what a Taylor series does, or what we gain from examining and working with Taylor series, then what would happen if instead of feeding into this this machine to produce a Taylor series, instead of feeding into it a function like sine of x that is not a polynomial, or natural log of x, or the square root of x, instead of feeding into this machine something that's not a polynomial, what if we feed into it a literal polynomial? Well, there's a couple different thoughts here, but whenever I pose this to my class, when I teach in person, generally most people come up with the answer that the Taylor series of a polynomial is actually the polynomial itself. And that is true. So looking back at this problem, remember, for Taylor series, in order to write down the Taylor series, in general, it's the nth derivative at our center value over n factorial x minus our center to the n from n equals 0 to infinity. So if we write this out, we'll have essentially the 0th derivative at our center over n factorial. Oh, not n factorial. I guess this would be what, 0 factorial? Yeah, 0 factorial times x minus c to the 0th plus f, the first derivative at our center, over 1 factorial x minus our center to the first power, second derivative at our center over 2 factorial x minus c squared plus, I'll go up to this third one here, and before I do the dot dot dots. So that's what this would look like. I'm just going to move my little wonky series up a little bit. Get a little lopsided when I write sometimes. Okay. So simplifying this, we have, well, the 0th derivative is just the original function. So the original function at our value of -2, this would just be f of -2. And then this term here would just be 1 due to the 0th power. So it's f of -2 plus our first derivative at -2 over 1 factorial, which is 1. And then we'd have x minus -2, so x plus 2, plus our plus 1/2 times our second derivative at -2, x plus 2 quantity squared, plus our third derivative times a 6, that's what 1 over 3 factorial is, so f triple prime at -2 times x plus 2 quantity cubed. So f of -2 is -2 minus -2 cubed plus our first derivative. So our first derivative, f prime of x, is 1 minus 3x squared. So this is 1 minus 3 times -2 squared, x plus 2, plus a half times our second derivative, so f double prime of x is negative 6x. So this would be a half times negative 6 times our input, negative 2. X plus 2 quantity squared. And a sixth times our third derivative, f triple prime of x, which is negative 6. So negative 6. And then we have x plus 2 cubed. Now I didn't include these higher order terms, but this next term would be 1 over 4 factorial, which is 24, 1/24th, f quadruple prime at negative 2, oops, times x plus 2 quantity, oops, hold on, wrong line, x plus 2 quantity to the 4th power. Well, notice over here, f quadruple prime of x is 0. And in fact, f to the n of x is equal to 0 for all n that is greater than or equal to 4. So essentially, this term here vanishes, and so do all the other terms. They are all 0 because of that reason. So our Taylor series actually goes from an infinite sum down to just a regular old finite sum. And when it comes to finite sums, there is no question of convergence. If a sum is finite, it's well defined and it converges. There's no question. So if you go through all these motions here, we effectively have negative 2, 3 negatives, and another negative is 4 negatives, which is positive. 2 cubed is 8, so negative 2 plus 8. And then here we've got plus, this would be 1 minus 2, negative 2 squared is 4. So then this would be 1 minus 12. And then here we've got x plus 2. Here we've got, let's see here, plus a half times positive 12. This quantity squared, so x squared plus 4x plus 4. Oops, it's supposed to be 4, not 4x. There we go. And here we have negative 1 times this x plus 2 quantity cubed. So this would be x cubed plus 6x squared plus 12x plus 8, I believe that would be. Check my math there, but I think that's good. And then we can continue. So this is 6, and this is a negative 11, so this is negative 11x, negative 22. These two give me a 6. So then we have plus 6x squared plus 24x plus 24 minus x cubed minus 6x squared minus 12x minus 8. So then the 6x squared and the negative 6x squared cancel with one another. And then here we have these two together give us a negative 23x, together with our positive 24x give us a single x. So it looks like we have an x. If we combine those terms, cancel, cancel, cancel. And then it looks like we have a, let's see here, negative 8 and 6 gives us a negative 2. And a negative 22, that gives us a negative 24, which cancels with this 24. So our constants all vanish as well. And then we're left with x minus x cubed, which is our polynomial. So the moral of the story is, you can think of Taylor series as a way of taking something that's not a polynomial and converting it into something that is a polynomial, albeit of infinite degree and possibly not converging everywhere. So if you start with a polynomial, there's no point, because you're going to have all of this arithmetic, all of this algebra, these derivatives, and this formalism, and at the very end of the day, it's just going to simplify into x minus x cubed, the polynomial that you began with.